So here's what we need to know about Chapter 13. We're talking about vector functions in curves in space. Vector functions in curves in space. So what we've described so far have been planes and lines, things that are pretty rigid. We're going to be talking about rigid shapes, but instead of having them go in one direction or go in a flat direction in lots of different ways on that plane, we're going to talk about things that could go like this. Whee, I'm tracing them out with my finger and they're going crazy. Or they're going like this, spirals, DNA helixes. A function is a rule that assigns to each element in the domain an element in the range. A vector valued function or vector function is simply a function whose domain is the set of real numbers and whose range is a set of vectors. We're primarily interested in three-dimensional vector equations. Can you also have two-dimensional vector equations?
Probably.
Sure, absolutely. We're particularly interested in three-dimensional vector equations. These are not so much of a stretch from what we've just done. We have R of t, we have f of t, g of t, h of t, and f of t is the x direction, g of t is the j direction, the y direction, sorry, and k the z direction. That's it. That's it. There's no special trick to that. There's no special trick to that. The domain of R consists of all the values of t for which the expression is defined. So what are we looking out for? If we're trying to find out where a function is defined, what are the two things that we usually try to avoid?
Zeros in the denominator.
Zeros in the denominator and...
Zero.
What's the other illegal activity that you guys don't like doing? We're dealing with the real numbers, kids.
Oh, unreal numbers.
Yes, so how do we generate imaginary numbers? Root a negative. So we're avoiding rooting a negative. So if we ask for a domain of a regular function, you're trying to avoid dividing by 0 and
Negative roots.
negative even roots, right, to be more specific. Is there anything added in? No, there's nothing that's added into finding the domain in 3 dimensions. So when you're finding the domain of a vector function, essentially you're just finding the domain of 3 things, finding the intersection of the domain of the x, y, and z components. That's it. Can you find the limit of a vector function?
Yeah.
Yeah, absolutely. What do you think you do when you find the limit of a vector function?
3 limits.
3 limits. Ooh, scary. It's the same thing. Yes, Josh?
Are we going to be worrying about in this?
What you need to know. A vector function is continuous at a if the limit as x goes to a of r of t is r of a. This is the same definition for continuity you had in 2 dimensions. There's no difference in continuity. If you can draw the vector curve without lifting up your pencil, it is continuous. So if you're approaching a certain limit from left and right, a certain x value, or a certain time t, and you are approaching what the function evaluates to at that t value, the function is said to be continuous at that t value or that a value, depending on how the function is defined. So a space curve could look like this. Here we go. Here's what a space curve could look like. It could be nice and curvy. You see that blue vector?
Yeah.
That blue, as t changes, what happens to that blue vector? As t changes, what happens to that blue vector? Does it stay the same or does it change? It changes. We're anchoring at the origin. As t changes, we have x written in terms of f of t, y written in terms of g of t, and z written in terms of h of t. So there's some function for each of them. So as t changes, this vector is going to get like the magnitude will increase, it'll turn, it'll go berserk, right? The space curve is what you get if you take the end of this vector, the tip of this vector, and trace it out. So if I have a little glowing dot at the end of my finger here, and this my elbow represents the origin, we trace the end of this vector. If you look at the path of where this light is going, that light forms the space curve. That the tip of the vector forms that space curve.
So there's a distance between all these.
To draw a picture, what could you do? What?
Make a chart.
Yeah, make a table of values, right? When t is 0, when t is 1, when t is 2, t is -1, t is -2, t is -3, and you have a set of points. Theoretically, could you graph each of those points in 3 space and then connect them with something?
Yeah.
Absolutely. Could this be ridiculously annoying and hard?
Yes.
Absolutely. Okay, so this right here is the vector equation. If we wanted to write the parametric equation for this space curve, how would we write it?
X equals 1 plus t, y equals 2 plus 5t, and z equals 1 plus 6t.
Exactly. There is a very close relationship between the two. Cosine ti plus sine tj plus tk. In this case, you might want to do an analysis of each of the coordinates, not just plot them. You're very rarely just going to plot points. Did we do that before when we were graphing surfaces? No, we didn't graph points. What did we graph? We graphed traces or rulings, right? And then we connected them with the wire frame, and then we know it kind of, it's going to be a hyperbolic paraboloid. In this case, plotting points can be somewhat helpful. Like knowing one of the points might be helpful, knowing two might be helpful, maybe three, but you might want to try an analysis that's a little better. That's a little better than that. So for example, let's take a look at, as t gets bigger, what happens to z?
Linear.
Yeah, it just goes up, right, at the same rate. As t increases, this thing just goes up, right?
Yeah.
So wherever the points are on the xy plane, every time you increase t, it's just going to go up. So it might bounce all over the place, but it's just getting higher and higher as t gets on. So as t gets smaller or negative, it's going to go down. We don't know what it's going to do. It might go crazy, right? If this, you look at the coefficient of x and the coefficient of y. So let's ignore this for a second. Just ignore it. Can you tell me a simple relationship between the x-coordinate and the y-coordinate that has to stay true on this one? Yeah.
One equals 1, it's the other one equals 0, and vice versa.
What?
Like, they're pretty much universal. So if one equals 1, the other one will be 0.
Exactly. If one equals 1, the other one equals 0. That's true. No. You're getting really close to what I want you to say. If the coefficient is cosine t... What? Yeah, you know this. You know this is true. Equals what?
1.
You know that cosine squared t plus sine squared t is equal to 1. What is that?
To form a circle.
This is a circle.
Radius is 1.
This is a circle with what?
Radius 1.
Radius 1. So if you looked straight down at this thing, the x and y coordinates are always going to be on what circle?
The radius 1 is
Around the origin, right? So what you know from this relationship is the following. You know that if you started with this isometric 3D graph, and some of you still were flipping this, ready? Z, x, and y. We go out here, we go out to there, we go out to there. We know that if you look down on this, the points are always going to be above or below that circle. So let's look at 1 point, for example. When t equals 0, what's cosine of 0? We get 1. What's sine of 0? And what's 0 of 0? 0. If we plug in 0. So we know that it's at 1, 0, 0, like that. What would be another good value to plug in?
1.
Really? You can evaluate cosine of 1?
Sorry, pi.
Or before we get to pi, what else could we do? Pi over 2, maybe? So how about time equals pi over 2? What's cosine of pi over 2? Really? 0.
I was thinking pi over 4.
Yes, we already determined in my AP Calculus class that one way I can lose faith in humanity is by asking general cultural questions and by asking basic trig functions. It took them literally 5 minutes to answer the question, the sine inverse of 1/2 is equal to...
30 degrees.
No. Sorry, sine inverse of negative 1/2. What is it? Or no.
Or pi. Oh no, it's
Keep going.
5 pi over 6.
Negative.
Pi over 6.
Again, losing faith in humanity. I need to stop asking basic trig. 7 pi over 6. It's got to be negative. It's got to be below the x-axis, right? I literally took a walk for 3 minutes, came back, and they're like, the answer is 7 pi over 6. I'm like, great, you just scored a 50% as a class. Okay, so it's 0. What's sine of pi over 2? 1. And what's, oh, pi over 2. That's how high it is. So it's 0 forward. It's 1 over, and how high is it? Pi over 2. So I actually should go up to right about here. So what does this curve do? It actually does this. It goes like this up to here. What's it going to actually do? It's going to spiral around. It's going to go up. It's going to go up around like this. And it's always going to be rising. It's always going to be rising. Why? Well, we know the rate of change of the z component is 1. It's always going to be rising.
Do you call that a vector?
This would be a space curve. This would be a space curve. That is correct.
It's not a function.
SAT question. How long is the line? 2 inches. Why? Because I measured it. Like, no, that's not that's not what they're asking you to do here, right? Find x. There it is. Yeah. There's a whole, they published a book like Great Student Answers. Yeah, they're fantastic. Okay. So the question is, how do we figure out where they intersect? How do we figure out where they intersect? If we were just staying inside rectangular coordinates, what might we do? Here's the plane. Here's the cylinder.
set them equal to
Just
each
set,
other.
well, we can't quite set, we can almost set them equal to each other. This one is what? 2y plus 2z, sorry, I mean, double this one, right? What do you end up with? You know, 2x squared plus 2y squared, therefore has to equal y plus z. Now the real question is, now here's what you have to be careful of. Have we over-described the intersection? What that means is the intersection might exist in that thing right there, but we might be describing more points than what exist on that intersection. For example, we might be describing something that goes crazy outside of it, but we might also get the edge. I mean, what I'm looking for is just this edge right here.
You have to set ground.
Well, I don't get why we could be over this.
I'm just telling you, you can just believe it for now, okay?
Oh, okay.
We could be over-describing it. Yeah. We have a plane and a cylinder. Just in terms of what?
X, Y, Z.
Nope. Just in terms of t. Just in terms of t. Again, in this equation, it only matters what t is. Are we okay? So with
With, like,
such that is this. Such that. Yeah.
so we could say R of T is blah, 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 blah,
Such that.
line, 0, comma.
As long as your handwriting is clear enough to allow that. Many of you don't have handwriting that is clear enough to allow that. It just looks like a big L, okay? That's be very neat.
Like
So
this.
for all x, there exists a unique n such that. Anybody know what that says right there? For all x, there exists a unique n such that. Draw that out for you. That says, for all x, there exists a unique n such that.
Can you finish the statement?
No, I'm just making something up. The point is, that's what they remember. This is for all, that's x, that means there exists, that means unique, that's n, and that's such that.
Is that notation important to learn in college?
Absolutely. You're going to write the same words over and over again, so you write that instead. You're going to write proofs out, and you're going to say the same thing 1,000 times, so what do they do instead? For all, done. QED, it's thus is proved. Limit definition of the derivative of a vector function. Exactly. The rate of change of r with respect to t, r prime of t, is equal to the limit as h goes to 0 of r of t plus h minus r of t over h. Graphically, it looks like this. Graphically, it looks like this. And this is really not anything earth-shattering for you. It's something you've seen before. But instead of 2 dimensions, it's written in 3 dimensions. So what are we doing? This is a secant line. A secant line is when you connect any 2 points on a function or a relation or a space curve. It's a secant line. So what are we doing to find this r prime of t? We're anchoring p, and what are we doing?
Moving Q closer. and
Moving
closer.
q closer to p by making h smaller and smaller and smaller. Is this any different than what you did in BC and AB calculus? No, it is not. So to estimate r prime of t, we can make a table of values. We're not going to do that so much. Instead, we're actually just going to find derivatives directly because you believe in the power product chain quotient rules. We're okay with that? You believe in those things? You're a firm believer? That's good. What is that in relation to that?
Unit.
That's the unit vector in what direction?
Tangent line.
In the direction of the tangent line at the point. So that would be the unit, you call it maybe the unit derivative? Because that right, is that a vector right there? Is that a vector? Yeah, what's the vector? It's r, what's the direction? R prime of t. But what's the magnitude of that?
One.
It's 1. So it's the unit derivative vector. We're not doing anything too new with that either. You okay there? Yeah, I know. It's right after lunch. It's tough. It's very tough, I know.
So warm.
It is. I'm sorry. It's just how it is. Now here's something else that's not super nothing too fancy should be going on. Nothing too fancy should be going on. You should find. Find the tangent vector at t equals 0, right? You need to find that first. Is plugging in 0 a nice thing to do here?
No.
So when t equals 0, what does r prime of t equal? 0, comma.
Yeah.
Isn't it 0?
It's
1 minus
1.
1 minus 0, you're right. It is 1. You're absolutely right. Plus what? Plus 2. Exactly. So what is the magnitude of r prime of? So that's r prime of not t 0, right? Is what? root 5. Exactly. So the unit tangent vector at t at 0 is what?
The vector times one.
Yeah, 0, 1 over root 5, comma.
So,
Exactly. There it is. Unit tangent vector going in the same direction. Yes, Josh?
This is a question on the test. Can we leave it like that?
Show that if the magnitude of r of t is a constant, then r prime is orthogonal to r of t for all t. Show that if the magnitude of r of t is a constant, if it doesn't change. So let's look at it in 2 dimensions. Let's look at it in 2 dimensions. So if r of t is in 2 dimensions, yeah, what do we have here? We could have a, b, if we wanted to. And if it's equal to, if the magnitude, what's the magnitude of that vector going to be? It's equal to a constant. So what's that graph going to look like in 2 dimensions?
circle.
It's a circle, that's correct. With a radius of what? Is it c or root c? What do you think? Is it c or root c? No,
C.
is it c?
Yeah.
Yeah, I think it's c. So it goes out c, it goes down c. So that's it right there. So it's saying r prime is orthogonal to r of t. How do we prove that? Yeah, but we need to know another vector.
The radius.
This. What kind of differentiation are we going to need to do? Implicit differentiation. So what's it going to turn into, Jeff?
You get 2 plus 2y 1
Equals.
equals 0.
So you know that x plus y prime is equal to 0. So what does y prime equal?
1 over x.
Josh, someone speaking, negative x over y. So y prime is equal to negative x over y. What does that? How does that help us? This isn't super complete, but do you get the basic idea of what we just did there? So basically, we just proved that all the tangent lines of a circle are perpendicular to the vector connecting the origin to that point on the circle. That's what we just showed. Are we okay with that? Let me see if I can stumble my way through it even more poorly. If you're given this right here, if you're given this equals a constant, can you square both sides? Yeah, why not? You know, you could square both sides. The magnitude squared, do you remember that the magnitude squared of a vector is what? No, it's the dot of itself. Do you remember that? Do you remember that?
Yep.
Is that correct?
How you prove the concept?
What could we do with that?
Because cosine theaters.
Well, yeah, we're not going to prove it, but what could you do from this? Any ideas?
Plug C.
Don't plug C in. We're trying to show what? We'd like to show that the derivative of r, so what could we do to both sides? You could take the derivative of both sides, right? What's the derivative of a constant?
0.
So we know that, no, the derivative of a constant is 0, right?
But isn't that going to be
What's the derivative of dot product? Do you remember?
No.
shouldn't it be 0? Because it'd be a scalar.
It's gonna be a
Oh.
So you get 0 equals 0.
0.
Well, it's a scalar, but it doesn't have to be.
Just go with it. That's one of the things we listed. If you take the derivative, what? We essentially did the product rule for dot products, essentially. But we have the same thing twice, right? So what's that equal? That's 2 r prime of t dot r of t, right? And we know that has to equal what? 0. The only way to get that to equal 0 would be if r prime of t dot r of t was equal to, so they must be,
Oh, that's so easy.
yes, it's easy if you know what to do.
I don't understand. I thought the dot product is always a scalar.
Yes, but if you're writing the dot product out in terms of a variable t, it doesn't necessarily have to, yes, it's going to equal 0.
Oh, but you still got 0 equals 0. Okay, makes sense.
It's still true, yes. Okay, yeah, it's an indefinite integral because it doesn't have any, no bounds, no limits of integration. Exactly. So let's actually do classwork from 2 sections. 4 questions from there. And
Oh, but you only have one class C in that case instead of 3 different class C.
yes, yeah. But you remember what you do with constants? Like, what can you do with constants?
Combine them.
In many different ways you can combine them. Exactly. In many different ways you can combine them. Okay, so that's what I'd like you to work on right now to get a handle on this. You can bounce around a little bit, but please work on that classwork right there, and then in a minute I'll give you the homework.